Okay, I'm going to repeat myself momentarily. What we use is, after the impedance meter, backed by the frequency meter, after touching the electrode to here, to the coil. This is a refractometer, but this is a light intensity meter on top of these neodymium magnets. We take the laser that's coupled to the light meter, intensity meter, so we know exactly how much laser light is being used before we induce the coil. Then we take this. This is a very sensitive optical to precisely tune the laser. You see that? This is for laser machining. So that beam is precise, because what's happening is the phonon resonance is not going in a Cooper pair that David LaPont from the primer fields would like you to believe. It's going in a helix, because we can literally see it. Because the beam, we can take the beam and turn this around and spread the beam, and it becomes a double helix once this is attached. Okay? So now the light is moving in a double helix. That is how we check the light. Then we come here on this coil. You see it has 2 positive and 2 negative inputs. So we can square Faraday. Put it in here. Now we calculate Planck. Both. Electron volts and joules. Then we come over here, because they're coupled together, and we take this reading. Then we stick the rod in here while it's hot, as quickly as we can. Now we have the near and far magnetic resonance. Then we can take that and calculate Planck on phonon resonance. When all that is good and said, we come over here and check the capacitance overrun by the impedance. Now we know that the laser just became magnitudes over unity. And how we found this out was, we took a laser, hooked it up to the cell, and watched it. We burned a hole in a lemon at 1,000 feet from burn the skin in an imprint, a perfect flower of life imprint in the lemon at 1,000 feet with 5 watts. That's technically impossible. The reason we did this is because we had a spying neighbor, and we popped their LEDs in their infrared camera from 3,000 feet away. Now, moving forward to more fun things. Then we come over here and we check the kilowatts on a polyphase watt meter, but it's a 2-element watt meter, so we can definitely know how many kilowatts we're producing. And I'm being nice at 44 kilowatts. Okay? That's 44,000 watts you just saw coming through that electrode, and the light energy that you saw off the light does not compute Faraday. It computes Maxwell Planck and the equations that I'm introducing you to, which are straightforward fixing Einstein. Then we come over here and we redundant the load ohms, so we know exactly how many ohms that we're using. Then we come over here to the Wheatstone bridge. Now this isn't just your average Wheatstone bridge. This is called a, I'm sorry, pardon me. Pardon me. I'm trying to be careful. This is called a cascade divider. And you see what it does? It divides the cascade all the way down. So our true resistance in superconductivity is, thank you to Dr. Arthur Devine for buying this piece of equipment from a scrapyard that can easily handle 300 volts up against ground. An SG1. Okay? Product of Germany. Our true ohms are point. You see the U? Micro. 0.01743 times Planck. Okay? And we can check all three values up against ground just to make sure we know what we're doing. Now, we have not disconnected the power or anything. Now we're going to come over here. Remember, superconductivity, they've been trying supercomputers, and they can only throw the energy. The world record is the length of a grain of rice for 0.75 of a second. The back EMF. Okay? Half-life of EMF. So before we couple to a power supply, you see this can be dead shorted. No problem. It doesn't matter if I use a standard power supply or if I use a regulated power supply based on Ohm's law, just for safety. This is a safety video. So this is how we couple to the power plants. Capacitive discharge, redundant rectified, high frequency magnetic switches. You can't get a better, and then backed with a fuse. Okay? You cannot get a better redundancy. Moving forward to something important. Russ Grease from RWG Research and I sat at Tesla Tech until 2 o'clock in the morning grinding this Da Vinci wheel. What this is, this Da Vinci wheel is a perpetual motion machine. You see how it doesn't work? But it's actually going full speed right now, and it's been going full speed for 400 plus years because it's a perpetual thinking motion machine. So Da Vinci knew that if you went up against the king, you were going up against his gold. And so he knew, the king knew this didn't work. So he gave this to all his disciples so that all of the people that were studying under Da Vinci could go ahead and think. And if the king's men came around and you were doing this, he knew that wasn't math and you didn't get your head cut off. We're still at that point today. We're at greed. Now, the last redundancy that we use outside of spectrometry and everything else is we use a nitrogen flow meter up against hydrogen deuteride because the specific gravity of nitrogen by volume is 78% of the Earth's air. So we want to make sure that we're going up against that, not just regular old oxygen. We want to go up against the nitrogen. Okay. Now, this wire is now superconductive. The wire is attached to the power supply, and then you can hear everything's on. The water inside of here is regular old oceanside seawater. And this is a picture to remind me of what we're trying to protect. The cyanobacteria in our water that gives us our oxygen. That's what we're trying to protect. Are we clear? I sure hope we are. Follow that on my CO2 capture page and we move forward. Now, here's the power supply. We're going to go ahead and I'm going to hook it up. First, I'm going to turn it off for safety. I don't need to, but I want you guys to be safe. I'm going to go ahead and hook that up. Now watch. This is seawater. Watch the electrodes. Boom. Instant hydrogen off of only the negative electrode. Now, always mark your containers. Mark your containers when you open them, so that you know, especially with potassium hydroxide, if it's sucked up too much water, okay? Because you don't want it to spontaneously combust in your lab. Now, here's what happens, okay? In regular electrolysis, they'll use a teaspoon of potassium hydroxide in the water to make electrolysis. We're going to do this the scientific method way. Watch. You see that? You see that? That's a definitely a dead short. You see that potassium hydroxide at the bottom? I guarantee you the temperature is going to go up. Okay? You see the temperature rise? And that's a dead short. This power is definitely safe. Now, one more time. You're in intermission, because there's proprietary things in the shop I don't want you to see. But this is what I want you to see. The generator is not hooked up. It is not turning. We've already turned the wire into superconductive wire. The motor is off. The fluorescent lights are off. And there's as much electromagnetism away from us as possible to avoid the antenna effect. Standing load, 25 millivolts. I'm sorry. Let me just click that to auto or manual. 25.5 millivolts. That is the definition of superconductivity, ladies and gentlemen. The ohms meter is off. Okay? Now watch. Here's the kilohertz frequency. Here's the percentage. You see that? 60 hertz AC. Spot on. And it's not moving. Now, would you please turn on the fluorescent light? Okay. Here's the fluorescent light trying to overpower my superconductivity, but we're not going to let it. Now, here's the kilohertz from the fluorescent light. Here's the percentage from the fluorescent light on AC. Now we're going to flip it. Nothing on the DC. Let's just check it. 0 hertz. Let's check the percentage. Apparently nothing. All lost. Safety. We are back to safety again. Okay? Would you do me a favor and turn on the light switch over there? One more. Okay. Now the oscilloscope is on. Here's what we're going to show you. This is what the power companies don't necessarily want you to be involved with. But this is just too bad. Okay? The power's off. Would you go ahead and flip that big old switch on the wall to turn on the induction? Okay. Now the power's on. But my millivolts haven't really changed much. You see how it went up a little bit? Because we're bouncing up against electromagnetism and we're still holding. We're going to go, yeah, we're fine. We're set at millivolts. Now we're going to go ahead and turn on the ohms meter to times 1 ohm. Okay. Not much changed. The millivolts went down because of the ohms meter. The draw. Now we're going to turn up the power. We're going to go back to 10 hertz again. Remember, the motor give me 1 second. Oh, I'm sorry. I got to push start. Okay. Right at 10 hertz. Remember, the power supply here is exactly timed with this motor and this generator. So when that says 60 hertz, this and this and this should be timed. Okay? But look at what's happened. We're at 30. 3 times over ohms. 30% efficient. Over the 30% loss. Squared from 9. 9 divided by 3 is 0 ultimately. Minus the ohms I just showed you. Now we're going to check the amps. We're drawing just about a half an amp. The power is off here, so we should not have any load. Now we're going to turn on the power full blast. This draws 692 watts based on 60 hertz. Now, here's the draw, because we haven't heated it up yet. Here's the load, because nothing's heated up yet. Now we're going to turn it until we get 60 hertz. sorry, 60 volts. We're now at 50 volts, but only 48 hertz. We're gonna go $60 volts, only 56 hertz. Now we're under load. We're drawing just under 2.8 amps. But we're producing 3 amps. However, the power companies don't want that. They want us to be 60 hertz. And they're going to do their best to give us 60 hertz. Now we're drawing 3 amps. But we're producing 3.5 amps under a cold heat soak. But look at our hertz. And now look at our volts. I'm sorry, look at the hertz. Now look at the percentage. We're square. 100% use of the power. No losses. Now there's the voltage. Effectively producing more amps and volts. And look at the temperature. Okay, now we're going to hook up under this load the oscilloscope. Perfect phase angle. Let's slow that down so we can look at it one more time under load. Watch the oscilloscope carefully. Look familiar? Look familiar? Does that look familiar? How about perfect heterodyne magnetoresonance, courtesy of Linear Paul Magnetism 4-phase plasma power. There's my volts. There's my hertz. There's my percentage. Perfect power. Now, let's go ahead and see what DC looks like. Bingo! Here's my DC. pulsing. 2 positive and 2 negative. 4 squared over Faraday. Now, there's my hertz. Perfectly in tune with my AC. There ain't no DC ripple over the AC. Now, there's my percentage. I'm okay with that loss. I'm okay with that. I'm okay. I'll give up a little. I can't be perfect, but the power sure can be. Okay, now we're going to take superconductivity and we're going to go boom. You hear that? Now we're dead-headed up against Faraday. What's my DC voltage? There's my DC voltage. That's all I'm using. Up against electromagnetism. There's my hertz. Pretty damn tight. And there's my percentage. I'm okay with that 0.% loss. I'm okay with that. Because I'm dead-headed up against electromagnetism. Superconductivity rolling over electromagnetism. In a Bose-Einstein condensate at room temperature. Now, there's the hertz. Everybody's square, right? Watch this. Let's just go full blast to make this a shortcut. How come my wire is not burning and smoking like my shunt? And the coil is definitely hot. There's my production amps. There's my draw. You see that? We're going dead head up against Faraday. Okay? Dead-headed up against Faraday. No problem. No problem. Thank you for watching and have a good day. This is safe power. We decided to go ahead and put a shatter shield up against the chain because we flipped the polarity in the motor. Now, instead of the impedance or the hysteresis fighting the coil, it's drawing and repelling the coil. So the motor is much more efficient now. And we didn't change anything. We just reordered the magnetic structure in the neodymium magnets. Okay? So I have to do this. I'm sorry. Here's the inside of the generator. Okay? About as tight a hysteresis as you can get because we've taken the neodymium magnets and squared them with the coil. Once again, thank you for watching, and this has been your introduction to superconductivity. Have a nice day, and I will talk to you soon. My name is David Allen Puchta, and I'm the inventor, founder, and CEO of ProtonSpinTechnology.com.